Welcome back, ladies and gentlemen. Here we will be looking at some ideas for the solutions to these three questions which were assigned. I will not go through the entire solution to the final answers, but I will try to give you some insight for each of these questions and let you finish them on your own. First, number 24. And in this question, we have this object that breaks into two pieces due to an explosion. Doesn't really matter what the object is, but before the explosion and then after the explosion, and it is broken into two pieces afterward. Boom. So we are asked for the ratio of the two masses. There's a little bit of information that we are given and that we can discern from these two situations. So before the explosion and after. Before the explosion, this object, as far as we can tell, has zero kinetic energy, and also it has zero momentum, as far as we know. After the explosion, there's object 1, or piece 1, and piece 2. And what we can say is that, well, now each of these pieces are moving, so each one will have a kinetic energy. There will be a kinetic energy of object 1, there will be a kinetic energy of object 2. Since each one is since each one is also moving, there will also be a momentum for 1 and a momentum for object 2. Now, here's one of the keys to this this problem that we have to do. Remember the goal, right? What we're looking for, the final answer that we need, is the ratio of the two masses. So we can just say, well, what if we just come up with the ratio of mass 1 to mass 2, right? So that's what we're shooting for. I recognize that mass is involved in the calculation for the momentum of an object and also for the kinetic energy of an object. And velocity is also involved in both of those values, but the relationships are a little different. So I need to try to find a way to sort of equate, not exactly equate the two, but work back and forth between the two. Now, as an aside, you should be able to notice something here. After the explosion, there is kinetic energy to our system, whereas beforehand, there was not. So kinetic energy is not conserved here. But here's the key for this, and the key will be in the momentum. And I want you to think for just a second before I tell you. I want you to think regarding momentum. What is it about momentum that we will use to our advantage here? So think about that. Try to come up with that on your own. Maybe pause the video, and I'll be continuing in just a moment. So think. Here you go. Pause. And coming back. So now, the key with this is that momentum is conserved. As long as the net force acting on our system is zero. So our system, well, the system is just that, right? And therefore, that's also the system. Okay, fine. But the force that is imparting energy to each one of these, you might think of it that way, it's an internal force. It is inside the system. It is coming from within the system. And so momentum will be conserved. The net force acting on the system is zero. So we do see that momentum is conserved here. And that's critical. So when momentum is conserved, the change in momentum is zero from a before and after kind of situation. And from that we can see, well, the initial momentum will therefore equal the final momentum and each one will be 0. So the total momentum beforehand will have to equal the total momentum after whatever happened. So that's fine, and what this means is now the final momentum, well, the final momentum is the sum of those two guys, right? So we have P1 plus P2, and that has to equal 0 because momentum here is conserved. And there's something that you have to work out here. You want to keep in mind the goal. So can you see a way to get this ratio out of this relationship? Okay, I want you to try to work further down through this and come up with some way to see this. Now, you won't see the actual answer. You won't see, well, what is the value of this ratio? That's not going to come out of this, but something else will. So work through that, and we'll come back to that. There's something else with this problem to consider. And it is that in the problem we are told the relative kinetic energies of these two objects. We are told that the kinetic energy of one of these objects is twice the value of the kinetic energy of the other object. And so when we set this up, we can set this up as a ratio, the kinetic energy of object 2 to object 1, and we're told that that is a ratio of 2. Brilliant. Now we do have to use this, and so here's what I'm going to do. I'm just going to expand each of these, and I'm going to say, well, the kinetic energy of object 2 is 1/2 m2 v2 squared, and the kinetic energy of object 1 is 1/2 m1 v1 squared. Awesome. Now there's something you want to see here, and I'll point out part of it for you. You want to recognize this right here kinda resembles the goal, except it's inverted, right? So there's a link I need you to make. The link between this ratio of the kinetic energies and what you get from expanding this a little bit and trying to show your goal in this relationship. And so I'm going to leave this to you. Of course, you obviously see a little bit cancels out, right? But I'm going to leave this to you. Work this through. Going with, I'll just use this. Going with this, and keep working, keep manipulating the parts of this equation, and see if you can get to something in this relationship that matches something from this relationship. And once you get that, you'll start to see, oh, I have a way to get my answer. Okay, so that's how you set this up. You have to get those two linked together. All right, that was number 24. So work on that, and give you the final answer. Now this one's not in the back of the book, so number 24, the answer. And so if you don't want to see this, stop the video if you want to try to work it out yourself. So the answers come in 3, 2, 1. Here we go. The answer is the ratio of M1 to M2 equals 2. That is the answer you need to get for question 24. All right. Thank you for watching. I'll have a new video for the next partial solution for you just coming up. Take care.